Welcome to This Explainer. Today, we're diving straight into the hidden mechanics of how large language models actually scale. If you've ever found yourself wondering why running these massive AI models is so incredibly resource-intensive, well, you are definitely in the right place. We're going to explore a breakthrough paper from researchers at UC Berkeley, Stanford, and UC San Diego. It introduces vLLM and a seriously clever computer science trick that practically saved the modern AI serving system. Okay, let's jump right in. Did you know that processing a single AI prompt can actually cost up to 10 times more than your standard keyword search query? 10 times. That is a staggering economic reality for cloud companies racing to provide hosted AI services. We're talking about needing massive arrays of extremely expensive hardware accelerators, like GPUs, just to keep up with everyday user demand. So it begs the obvious question, why? What makes it so incredibly expensive? Well, the culprit isn't just the crazy heavy math happening behind the scenes with billions of parameters. It's actually a critical hidden bottleneck in how an AI manages its memory while it's running. Simply put, the system's serving throughput is inherently memory-bound.
Section 1. Meet the KV cache, the AI's memory bank. To really grasp this bottleneck, we have to look at how these language models actually write. They don't just spit out a whole essay at once, right? They generate text sequentially, literally one word or token at a time. And to pull that off, the model has to remember every single thing it just read and wrote. It uses a dynamic memory bank called the KV cache, or key value cache. But here's the catch. This cache grows unpredictably, and man, it grows incredibly fast with every single token generated. Just look at this layout for a 13 billion parameter model running on a standard NVIDIA A100 GPU. The model weights take up about 65% of the space, sure, but look at that massive red section. Up to 30% of the GPU's memory is just devoured by the KV cache. This massive footprint severely limits how many user requests we can batch together and process at the exact same time. Section 2. The fragmentation problem. Invisible waste. But the real villain here isn't just the sheer size of the cache. It's how horribly inefficient older serving systems are at managing that space. These older systems try to pre-allocate massive, contiguous chunks of memory by guessing the absolute maximum possible length of a prompt. It's kind of like a restaurant reserving an entire 50-person banquet table for guests who might just be eating alone. The result? A mind-boggling amount of empty, wasted space, which is categorized as reserved memory, internal fragmentation, and external fragmentation. So here's the kicker. By forcing this contiguous memory allocation, these older systems essentially shoot themselves in the foot. Since an AI's output is rarely the absolute maximum length, internal fragmentation just runs rampant. Combine that with external fragmentation from dealing with different request sizes, and researchers found something shocking. Only about 20 to 38% of the KV cache memory is actually used to store real token states. That means, practically speaking, up to 80% of an insanely expensive GPU's memory is just sitting there, completely empty, completely useless. Section 3. Enter Paged, an OS-inspired hero. So, how on earth do we fix this massive waste? Because, let's face it, we can't just keep buying more GPUs forever. Well, a brilliant team of researchers introduced a concept called PagedAttention. This algorithm completely ditches the old requirement for contiguous memory. Instead of demanding one massive, unbroken chunk of space, PagedAttention chops the KV cache up into smaller, fixed-sized blocks. These blocks can be stored absolutely anywhere in the physical memory, and they're only allocated dynamically, right when they are actually needed. Now, if this sounds a bit familiar, you hit the nail on the head. It completely repurposes a classic 1960s operating system concept, virtual memory and paging. By bridging traditional computer science with cutting-edge AI, we can basically think of these KV cache blocks as memory pages, the tokens as bytes, and the user requests as OS processes. It's a remarkably elegant translation that allows the vLLM serving engine to achieve near-zero memory waste. Section 4. Unlocking Advanced Memory Sharing, the Superpowers. This block-by-block approach doesn't just save space, though. It actually unlocks some serious superpowers for language models. Because memory blocks are now separated and mapped dynamically using a block table, vLLM can effortlessly share pieces of memory across different sequences. This is an absolute game changer for complex decoder algorithms used in the real world. We're talking about parallel sampling, where an AI coding assistant generates multiple outputs from a single prompt, or beam search for machine translation, or even shared prefixes for system instructions.
To see how a shared prefix works in practice, take a look at a machine translation task. The system prompt that gives the AI its initial instructions, it only needs to be stored in the physical memory exactly once. It doesn't matter if there are 2 parallel translations happening or 1,000, they all just point right back to the exact same physical blocks for that shared prefix. And to manage all this sharing without data corruption, vLLM uses a really clever copy-on-write mechanism. Physical memory blocks are safely shared across requests, and the system only creates a new separate physical block when the sequences finally diverge and need to write new different tokens. The research shows this practically eliminates redundant duplication, saving up to 55% of memory usage in heavy tasks like beam search. Section 5. Massive performance boosts, the tangible impact. So what happens when you combine this PagedAttention algorithm into the vLLM serving engine? Since memory fragmentation is practically wiped out, you can do massive batching. On a dataset of real ChatGPT conversations called ShareGPT, vLLM was able to batch an average of over 30 requests at a time. That means fitting significantly more requests into the exact same hardware compared to previously highly optimized systems like Orca, which only managed about 13. And on the Alpaca dataset, the gap is even crazier, jumping to over 132 batched requests at once. The ultimate takeaway from the researchers' evaluation is simply undeniable. vLLM improves overall throughput by 2 to 4 times over existing systems like Orca and an unbelievable 22 times over systems like Faster Transformer. And the absolute best part? It pulls off this massive speedup without losing a single drop of model accuracy. This elegant, old-school OS-inspired solution fundamentally transforms the economics of AI. It wrings every single ounce of utility out of incredibly expensive GPU memory. And it leaves us with one fascinating question to ponder. With the KV cache memory no longer the severe bottleneck it once was, just how much larger, faster, and smarter will our next generation of language models be? Thanks for joining me for this explainer, and I'll catch you in the next one.